Welcome back to AI Paper Podcasts. Today, we're diving into a paper that's making a serious splash in the world of image generation. It's called Visual AutoRegressive Modeling, Scalable Image Generation via Next Scale Prediction. And, the diffusion models are the be-all and end-all. Think again.
Yeah.
This paper argues that their new method, VAR, blows diffusion transformers out of the water, not just in image quality.
Yeah, it's true. This paper is making some bold claims. They're saying VAR is faster, more data efficient, and scales better. We're talking up to 20 times faster inference speed compared to traditional autoregressive models. And even better FID and IS scores than diffusion models on ImageNet benchmarks. They even found evidence of power law scaling, suggesting we could see even bigger leaps in performance as models scale up. Plus, VAR can do more than just synthesize images. They show promising results in zero-shot tasks like in-painting, out-painting, and class-conditional image editing. This could be a real game changer in how we think about image generation.
So no more agonizingly slow image generation. That's music to my ears.
You and me both. But let's not get ahead of ourselves. Let's dive into the paper and see how they actually achieve this.
All right, let's start with the problem statement. As AI practitioners, we all know traditional autoregressive models for image generation have some serious limitations.
You're telling me, I think we've all struggled with those limitations at some point. The way they typically tokenize image features into a 1D sequence just doesn't jive with the inherent 2D structure of images.
Right, it's like trying to shove a square peg into a round hole.
Exactly, and this leads to a whole host of problems. It violates the mathematical premise of unidirectional dependency, messes up the spatial relationships between pixels, and is computationally inefficient to boot. We're talking ON6 computational costs for an NXN image.
Yikes. No wonder those models are slow. So how does VAR address this fundamental issue? What's their secret sauce?
Their secret sauce is a clever idea they call next scale prediction. Instead of predicting individual tokens in a sequence, they predict entire token maps at progressively higher resolutions.
So instead of building a puzzle piece by piece, they're building it block by block.
Precisely. Imagine starting with a super low resolution representation of your image, like a blurry thumbnail. Then the model predicts the next level of detail, filling in more and more information until you have a full high-resolution image.
I see. It's kind of like building a house from a blueprint. You start with the overall structure and then add more and more detail until you have the finished product.
That's a great analogy. And this approach elegantly sidesteps all those issues that plague traditional AR models. By working with multi-scale representations, they preserve the spatial relationships in the image data, satisfy the unidirectional dependency premise, and significantly reduce the computational cost to ON4.
Okay, that's a pretty hefty speed boost. And they managed to do all of this while also achieving better image quality.
That's what they claim. And their experiments seem to back it up. They put VAR through its paces on ImageNet, and the results are pretty impressive.
All right, let's get into the nitty-gritty. What kind of results are we talking about?
Well, on the 256 by 256 benchmark, their VAR model achieves an FID score of 1.73. To put that into perspective, some existing AR methods have FID scores in the double digits, and even diffusion transformers score around 2.1 to 2.3. They saw similar results on the 512 by 512 benchmark, indicating that VAR's performance holds up at higher resolutions.
Wow, that's a significant improvement. So not only is it faster, but it also produces better-looking images.
Exactly. And it's not just about FID scores. They also report significantly higher IS scores, indicating that VR generates more diverse and realistic images compared to other methods.
Okay, color me impressed. But let's talk implementation for a bit. They mention a two-stage training process, right? Can you walk us through that?
Sure. The first stage involves training a multi-scale VQVAE. Think of this as the tokenizer that encodes the images into those multi-scale token maps we were talking about. They use a slightly modified version of the VQVAE architecture from the VQGAE paper.
Okay, so that's how they build their image pyramid. What happens in the second stage?
That's where the magic happens. They train a VAR transformer, similar in structure to GPT-2, which takes those multi-scale token maps and predicts the next higher resolution map. It's like a cascade of predictions, each one refining the image further.
Interesting. Did they do anything fancy with the transformer architecture, or did they keep it relatively straightforward?
They actually kept it surprisingly simple. They deliberately avoided some of the more complex techniques used in large language models. They wanted to see how far they could get with a more basic design, and clearly it worked out pretty well for them.
It's amazing what you can achieve with a solid foundation and a clever idea.
Absolutely. But there's another aspect of this paper that I think is particularly intriguing, the scaling laws.
Ah, yes, scaling laws. Everyone's talking about them these days, especially with the rise of large language models. What did they find in terms of scaling laws for VAR?
Well, they investigated how VAR's performance scales with model size and training compute, and guess what? They found clear evidence of power law scaling. As they increased the model size or the amount of training compute, the test loss decreased predictably according to a power law, just like we've seen with large language models.
So bigger models and more compute lead to better performance, and we can even predict how much better based on these scaling laws.
That's exactly right. And this is a big deal because it suggests that VAR's performance isn't going to hit a ceiling anytime soon. As we develop larger models and more powerful hardware, we can expect VAR to continue to improve, potentially leading to even more impressive results in the future.
Now that's what I call promising. Okay, so we've covered the limitations of traditional AR models, VAR's novel approach, its impressive performance, and its potential for scaling. But can it do more than just generate pretty pictures on ImageNet?
That's a great question, and the answer is a resounding yes. In fact, that's what I find most exciting about this work. They show VAR's capabilities in several zero-shot tasks, demonstrating that it's not just a one-trick pony.
Okay, you've got me hooked. Tell me more. What kind of zero-shot tasks did they explore?
They tested VAR on in-painting, out-painting, and class-conditional image editing, and the results are pretty remarkable, especially considering the model wasn't explicitly trained for these tasks. For example, in the in-painting task, they showed VAR can realistically fill in missing parts of an image, blending seamlessly with the existing content. And in out-painting, it can extend an image beyond its original boundaries, creating new content that's consistent with the overall scene.
So it's not just copying and pasting, it's actually understanding and generating new content that makes sense.
That's right. And perhaps most impressively, in class-conditional image editing, they demonstrate VAR's ability to modify objects within an image based on a specific class label. Imagine being able to tell the model, make that dog a poodle, and it actually does it convincingly.
Wow, that's next-level stuff. Yeah. It sounds like VAR is more than just an image generator. It's a tool for image manipulation and even a form of visual understanding.
I couldn't agree more. And this versatility stems from the core principles of VAR's design: next scale prediction, the preservation of spatial relationships, and a scalable architecture.
This is all incredibly exciting. But before we get too carried away, did the authors conduct any ablation studies to really understand which components of VAR are driving these impressive results? Good science and all that?
Absolutely. They're very thorough in their analysis. They did a series of ablation studies systematically removing or modifying different components to isolate their individual contributions. And their findings are quite insightful. For example, they found that adaptive layer normalization plays a crucial role in boosting performance, and that top-height sampling during generation helps the model produce more realistic and coherent images. They also showed that classifier-free guidance leads to substantial improvements in FID scores.
So it wasn't just luck or throwing everything at the wall and seeing what stuck. They carefully analyzed the impact of each design choice.
Exactly, and this attention to detail makes their findings even more compelling. It's not just about showing that VAR works, it's about understanding why it works and how we can make it even better.
Now, you mentioned that one of the limitations of VAR is its reliance on the existing VQVAE tokenizer. Do they discuss any potential improvements or alternative approaches?
They do. They acknowledge that the tokenizer is a critical component and that exploring more advanced tokenizer techniques could further enhance VAR's performance and efficiency. They point to some recent research in this area as a promising direction for future work.
Interesting. So there's still room for improvement even at the ground level. But overall, it sounds like they're pretty optimistic about VAR's potential.
They are, and I have to say, their enthusiasm is contagious. This paper is a real breath of fresh air in the field of image generation, and I'm eager to see where this research leads. It's definitely a paper that anyone working in this area should have on their radar.
I couldn't agree more. All right, so we've covered a lot of ground in this first part of our deep dive into VAR. We've seen how it addresses the limitations of traditional AR models, its impressive performance on ImageNet, its capabilities in zero-shot tasks, and its potential for scaling. But there's more to unpack. In the next part, we'll delve deeper into the specifics of their implementation, their findings on scaling laws, and those exciting zero-shot applications in more detail.
Stay tuned, folks. There's much more to come. So you ready to dive back into the world of VAR?
Absolutely. I'm particularly interested in hearing more about those scaling laws. It's fascinating how they're finding these power law relationships in different areas of AI. It really speaks to the power of scale in machine learning these days.
Its true scale is changing the game. And the fact that they found evidence of power law scaling in VAR is incredibly exciting. It suggests that we're just scratching the surface of what's possible with this approach.
All right, so they trained a bunch of different size models ranging from millions to billions of parameters and tracked the test loss as they scaled up. What did the graphs look like? Were those power law relationships obvious?
They were strikingly clear. When they plotted the test loss against the number of model parameters or the training compute, it formed a near-perfect straight line on a log-log scale. We're talking Pearson correlation coefficients close to 90.998.
Wow, that's almost a perfect correlation. That's pretty strong evidence for power law scaling.
It really is. And what makes this even more compelling is that they observed a similar power law relationship for the token error rate as well. So as the models scale up, they're not just getting better overall, they're also getting better at predicting individual visual elements.
That makes sense. The more data the model sees, the better it gets at understanding the finer details of images. It's like a painter who, with more practice, not only improves their composition, but also their brushstrokes.
Exactly, and the paper includes a figure showing generated samples from different size models at various stages of training. It's really cool to see how the images become sharper, more vibrant, and more realistic as the model scales up and learns from more data. It's a visual demonstration of the power of scale.
Okay, so scaling is definitely a key takeaway here, but before we move on, I want to go back to something you mentioned earlier, the simplicity of VAR's architecture. They intentionally avoided using some of the more complex techniques that are popular in large language models. Why do you think they made that choice?
I think it was a strategic decision. They wanted to demonstrate the power of the core VAR concept, the next scale prediction, without relying on bells and whistles. By keeping the architecture simple, they could isolate the impact of this core idea and show that it's enough to achieve state-of-the-art results.
It's like they were saying, look, we can get amazing results even with a relatively straightforward approach.
Right. And it also sets the stage for future work. Now that they've established a solid foundation, researchers can explore how incorporating those more complex techniques might further enhance VAR's capabilities.
That makes sense. It's a smart way to lay the groundwork for future innovation.
Yeah.
So speaking of innovation, let's dive deeper into those zero-shot tasks you mentioned earlier. These seem like the real bread and butter of what makes VAR so exciting.
Absolutely. Zero-shot learning is one of the most promising frontiers in AI, and VAR seems to excel in this area. Their experiments with image in-painting, out-painting, and class-conditional image editing really showcase VAR's versatility and its ability to generalize beyond the specific task it was trained on.
All right, let's start with in-painting. I'm sure everyone's familiar with those restore old photos apps that magically fill in cracks and tears. Is that basically what VAR is doing here?
It's similar, but VAR's capabilities go beyond simple restoration. They gave the model images with portions masked out and tasked it with generating the missing content. And VAR didn't just copy and paste textures, it generated content that seamlessly blended with the existing image, respecting the context and the overall composition.
So it was like VAR was understanding the scene and filling in the blanks in a way that made sense.
Exactly. It was able to extrapolate information from the surrounding pixels and generate new content that was both realistic and consistent with the overall image. It's a powerful demonstration of the model's ability to understand and manipulate visual information.
That's impressive. And what about outpainting? How did VAR handle extending images beyond their original boundaries?
It did remarkably well. They presented the model with an image and asked it to extend the scene outwards, essentially imagining what lies beyond the frame. And VAR produced realistic extensions that continued the existing visual themes, creating new content that felt coherent and consistent with the original image.
So it wasn't just repeating patterns, it was genuinely extending the scene in a creative and plausible way.
Exactly. And what's fascinating is that this capability wasn't explicitly programmed into the model. It emerged organically from VAR's training on ImageNet and its ability to learn and generalize patterns from that massive dataset.
It's a testament to the power of deep learning, to uncover and exploit hidden structures in data. Now let's talk about the most intriguing zero-shot task of all, class-conditional image editing. This one really pushes the boundaries of what we typically think of as image generation.
I agree. This task is all about manipulating specific objects or elements within an image based on a given class label. It's like having a visual editor that understands the semantic meaning of the elements it's working with.
So instead of just saying, make this image brighter or crop this image, you could say, make that dog a poodle, or change the color of that car.
Exactly, and that's precisely what they demonstrated in the paper. They showed that VAR can modify objects within an image while preserving the background and the overall composition. For example, they could change the breed of a dog in an image while leaving everything else untouched.
That's incredible. It's like VAR has a built-in understanding of the relationships between objects and categories.
It's a level of visual understanding that we haven't really seen in previous image generation models. It's a significant step towards bridging the gap between visual and semantic information.
And what's even more amazing is that VAR achieved these results without any specific fine-tuning for these zero-shot tasks. It suggests that the knowledge and understanding it acquired during training on ImageNet is somehow transferable to these new and unseen situations.
It's a testament to the power of deep learning to learn generalizable representations of the world. And it opens up a whole new realm of possibilities for how we can use and interact with images. Imagine being able to easily edit images based on natural language descriptions. You could say, make the sky blue and add a few fluffy clouds, and VAR could execute those instructions with precision and creativity.
It's like having a visual translator that can understand and manipulate images based on human language. The possibilities are truly mind-boggling. Now, we've talked a lot about the successes of VAR, but it's important to acknowledge that no scientific endeavor is without limitations. Did the authors address any areas where VAR could be improved or expanded upon?
They did, and I commend them for their transparency. They openly acknowledged that their current work is just a starting point and that there are several avenues for future research and development.
Okay, so what are some of the areas they highlighted for further investigation?
Well, as we discussed earlier, one of the main limitations is the reliance on the existing VQVAE tokenizer. They acknowledge that exploring more advanced tokenizer techniques could potentially unlock further improvements in VAR's performance efficiency and scaling behavior. It's like they're saying, we've built a fantastic engine, but now let's find even better fuel to power it.
That makes sense. The tokenizer is the foundation, and a stronger foundation could lead to even greater heights. What else did they mention?
Another area they highlighted is the lack of text prompt generation in their current implementation. Right now, VAR requires image inputs to generate variations or edits, but they recognize the value of being able to generate images directly from natural language descriptions.
Right, that's the holy grail of image generation, being able to turn words into pictures seamlessly.
Exactly. And while they haven't implemented this capability yet, they're optimistic that VAR's architecture, which shares similarities with large language models, could be adapted to enable text-to-image generation. They even hint at some potential approaches for integrating VAR with LLMs to achieve this goal.
So it's not a fundamental limitation, it's an exciting challenge for future work. They're essentially saying, we've built this amazing visual toolbox, now let's connect it to the language processing engine.
Precisely. And that connection between vision and language has the potential to be truly transformative. Imagine being able to describe a scene in detail and having VAR generate a photorealistic image that perfectly captures your vision. It could revolutionize creative industries, enhance communication, and even lead to new forms of art and expression.
It's like giving everyone the power to be a visual storyteller, regardless of their artistic skills. But there's one more potential application of VAR that I'm particularly excited about: video generation. Do they discuss that possibility at all?
They do. They briefly mentioned the potential of extending VAR to video generation, and I think it's a natural next step. After all, video is just a sequence of images, and VAR's ability to handle temporal dependencies and its efficiency make it well suited for tackling this challenge.
I'm already imagining the possibilities. Imagine generating high-quality videos from text prompts, or even manipulating existing videos with VAR's understanding of visual content.
The possibilities are truly endless, and I'm eager to see how researchers explore this exciting frontier.
All right, well, I think we've covered a lot of ground in this second part of our deep dive into VAR. We've delved into the details of its architecture, its impressive scaling behavior, its remarkable capabilities in zero-shot tasks, and the exciting directions for future research.
It's been a fascinating journey so far, and I'm ready for the final leg where we'll wrap up our discussion and explore the broader implications of this groundbreaking research.
Lead the way. I'm eager to hear your final thoughts on VAR and its potential impact on the world of AI and beyond. So we've seen what VR can do, how it works, and where it might be headed. But let's zoom out for a moment and consider the bigger picture. What are the broader implications of this research? Could this signal a shift in the landscape of image and video generation?
I think it has the potential to be a real turning point. For a while, diffusion models have been the dominant force in image generation, and they're incredibly powerful, no doubt. But VAR offers a compelling alternative one that addresses some of the key limitations of diffusion models while also opening up new possibilities.
Right, like the speed improvements and the potential for even better scaling.
Yeah.
And those zero-shot capabilities are pretty mind-blowing. It
Yeah.
feels like we're moving beyond just generating pretty pictures and towards a deeper understanding of visual information.
I completely agree. VAR seems to be learning something more fundamental about how images are structured and how they represent the world. It's not just mimicking patterns, it's understanding concepts and relationships.
And that understanding is what enables it to perform those impressive zero-shot tasks.
Right.
Right? It's like it's learned a visual language that it can then apply to new and unseen situations.
Exactly. And this ability to generalize is crucial for any AI system that we want to deploy in the real world. We
Yeah.
can't train models on every possible scenario, so they need to be able to adapt and learn from new experiences.
This paper really has me thinking about the future of creative AI. Imagine a world where anyone can describe a scene or an object in detail and have an AI system generate a photorealistic image or even a video that perfectly matches their vision. It could democratize creativity and empower people to express themselves in entirely new ways.
It's a tantalizing prospect, isn't it? And I think VAR is a significant step towards realizing that vision. Of course, there's still work to be done, especially in areas like text prompt generation and video generation, but the foundation is there and the potential is enormous.
I'm also curious to see how VAR might impact other areas of AI research. Could this idea of next-scale prediction be applied to other domains beyond vision? What about audio generation, natural language processing, or even robotics?
That's a great question. It's definitely worth exploring whether the principles behind VAR could be generalized to other types of data. Could we develop similar hierarchical multi-scale models for audio text or even 3D models? It's a fascinating avenue for future research, and I wouldn't be surprised to see VAR-inspired approaches popping up in other fields in the coming years.
Well, it certainly seems like the authors of this paper have opened up a Pandora's box of possibilities. They've not only presented a powerful new approach to image generation, but also sparked a whole new wave of research questions and potential applications.
And that's the hallmark of truly groundbreaking research. It's not just about solving a specific problem, it's about changing the way we think about a whole field of study. And I think VAR has the potential to do just that.
I couldn't agree more. It's been an absolute pleasure diving into this paper with you. I'm walking away with a renewed sense of excitement about the future of AI and the incredible things we can achieve when we combine creative ideas with rigorous research.
The pleasure was all mine. And to all our listeners out there, if you're as intrigued by VAR as we are, be sure to check out the full paper. The link is in the show notes. And let us know your thoughts on this groundbreaking research.
Absolutely. We always love hearing from our listeners. And until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with AI.